In order to address problems with issues with correlated data and non-stationary distribution, the authors suggested or introduced an experience replay mechanism where we store all of our previous transitions or some number, a fixed number of our previous transitions, and from our past experience. And at each time step, we randomly sample and train on previous transitions that are randomly sampled from all of our previous experience. This results in smoother training distribution over many past behavior, and it also helps decorrelating the observations, right? So we don't necessarily take successive transitions from successive time steps, but we randomly pick transitions from all of our history or some truncated history, usually. So we use this transition in order to train a specific function approximator, that represents Q values, right? So it approximates our Q approximator Q hat tries to eventually, or we try to learn or to train it to fit the Q star values. And we do this using off-policy learning with value propagation, right? One-step TD learning, where we set our target value, our Q star value, to be, or we define it through the expected next state that we're going to see after visiting state S and taking action A, the expected immediate reward, and the action that maximizes the Q star value in the next state S prime. Okay? In this case, in this equation here, this large epsilon, small sigma, right? This is a small sigma, I think, represents the environment, the underlying MDP. Okay, so I'm trying to keep the exact same notation from the DQN paper, so it will be easier for you to go back and read that paper using exactly the same notation. So we update our Q network, our Q approximation at each step in the environment, right? Using stochastic gradient descent with squared error loss, right? So here is our loss function, the definition of our loss function, the squared error loss function, again using the same definitions, the same notation as in the paper, and our label, the yi, what we're trying to fit with our function approximator, with a Q approximator, is the value, a single sample from the definition of a one-step lookup, right? So the immediate reward plus the maximal discounted Q value in the next state. Here in this, the notation here includes the raw of S of A. This is the behavior distribution. For instance, an epsilon greedy. This is what they used in the paper. And theta I minus y is considered, that would be the assignments to the tunable parameters in our deep neural network. These are weights and biases usually. This is considered fixed when we optimize the loss function right here. And this will help when taking the derivative with respect to theta, and also it helps us with stable learning. So now we define the loss function, so we can easily now also define the gradient of the loss function, right? So this is the gradient of the squared error loss. We've seen this before when we discussed Q learning with approximation, or TD learning with approximation. And of course, though, now we also need to define the gradient of our Q approximation, right? Previously, we mainly saw this term here as maybe just our input features when we used linear approximations. But in this case, of course, we have a more complex definition of the gradient of our deep neural network estimator, the approximator. But we know how to do that using the how to compute all of this gradient, all of the partial derivatives of theta I, using the back propagation algorithm that we previously covered. Right, and then compute all of the gradients for all of the weights and biases in our deep neural network. And now we're ready to go over the pseudocode for Q-learning with experience replay. This is the DQN algorithm that you'll also be implementing in your home assignments. So initially we initialize the replay memory, right, that contains all of the transitions that we've seen so far. Usually, as I said before, we have some capacity to the replay memory. We set it to some capital N. It should be large, but usually, specifically if we're continually learning, we can't have it, at some point we'll just deplete all of our memory. So, and in many cases we also want to forget, in some cases where we are highly, where our policy changes dramatically, actually we would like also to keep a smaller replay memory to allow us to forget previous transitions, previous state distributions. We also, so we initialize our replay memory and two identical Q approximators that are convolutional neural networks, right? Q and Q hat. In both cases, both of these are deep neural network approximators. We just keep two copies of this, one with tunable parameters theta, and the other will just say that the tunable parameters of theta are minus, right? And initially we just set them to be identical. And actually every once in a while we'll just set them to be identical, and you can think of Q hat as an identical copy of Q, but a delayed copy. And I'll explain later on why this is beneficial to do. Why keeping two of these networks is beneficial. Then we start our training process. We play M different episodes. Let's say we have M training episodes. These are full games in the environment, in the video game environment. We start from some episode X1. This is our initial screen at the beginning of the game. And then we progress. And then we do, what they suggested doing is some pre-processing to the state, right? As I said, we discussed it previously when we discussed the Markovian property. Just defining a state as the single image that we see on the screen at the current time step might not be sufficient in order for us to infer, for instance, movement of a ball or something like that. And also, it's not very computational efficient. There's a lot of information that we don't really need there, which can slow down learning or slow down training of a large convolutional neural network. So what they propose doing is to do some processing on the image, on each image and at each state, where we include the four last frames, right? Four last image frames. This will help us to provide some information regarding movement, for instance. And also we perform grayscaling, so instead of using colors, RGB matrices for the image, we simply do grayscale conversion. This helps a lot with more efficient data management. We also do downsampling and cropping, so a lot of the image during the game is like the borders or stuff that are not really important for learning how to play the game, and so we simply clean those out. And again, this helps with to be more computationally efficient. Next, then during the episode, at each time step, what we do is with some small probability we select a random action. This is our exploration. Otherwise, we select the currently known best action, right? We exploit our current knowledge. This is simply an epsilon greedy exploration strategy, as we've seen previously. Then we execute the chosen action and store the processed observed transition in the replay memory. Okay, so unlike the algorithms that we've seen previously, at this point we don't obtain each one of our sample transitions and directly learn from it or apply it to train our function approximator, but we simply store it in our large replay buffer. And then in order to decorrelate the samples, what we do is we sample a random mini batch of transitions from our replay memory. So this might or usually does not include the last transition that we just saw. It includes many transitions that are, hopefully, if we're going over our entire history, that are come from different episodes in different locations, and so this helps us to get decorrelated samples. Then we do the experience replay. That is, we sample the random mini batch of transitions from the replay memory, and we perform gradient descent step on Q, our Q network, right, the one here on top, and not on Q hat. And then once every several steps, which is a hyperparameter, C, we set the target function, Q hat, to equal Q. Okay, so at the end of the day, we're training two Q networks where one is just a delayed version of the one that we are constantly updating. Why is that important? So I just copied the text from the paper, exactly answering this question, or exactly how they explain it. So they say, this modification makes the algorithm more stable compared to standard online Q learning, where an update that increases Q, the Q network, often also increases, the Q estimation for some state and action pair also increases the Q estimation for nearby states. Specifically in our transitions, we update state ST, but we do it based on our approximation at ST plus 1, right, at the next state. And this leads to a lot of unstable updates or unstable learning. Hence, this will also increase the target Y value. And in many cases, this leads to oscillations or divergence in the policy. Okay, so in order to avoid that, they did this trick of keeping two Q networks, where one is a delayed update, one is continually being updated, but the other is a delayed update of the one continually being updated. And of course, it's very important that when we set our target Q value, when we compute Y, we use the delayed network, the Q hat, our target network. Okay, any questions?
Well, previously we saw that for TDE learning approaches, they suffer from bias. Mm-hmm. But how does this approach address that?
This also suffers from bias. Okay, we have an estimation, we have a nonlinear approximator, bias is baked in. Okay. It didn't solve the bias issue.
So we saw that eligibility traces help. Why not use that here?
Why not use eligibility traces? Because they are on policy, and this is an off-policy algorithm. You could, right, previously we saw that we can use them to some extent to get maybe better estimation of Y's, no, but maybe bias, depending how you do the, what do you do once you go off policy? You could try it, you know what, you could try it and see empirically. You won't have any theoretical assurances. You don't have any theoretical assurances for DQN as is, right? But it might work well in some domains. It might actually be a nice course project if someone is interested in doing that. Just trying to incorporate eligibility traces into DQN and see when and where it might be beneficial.